my name is Tanvi Batra, and my mentor for this paper was Dr. Tim Tomei. And today I will be presenting my research, which is using the IBM quantum composer to study gravitational waves, or LIGO, through quantum interference. So this topic was actually inspired by my mom. She did research when I was like 8 years old with Caltech using the LIGO observatory. And essentially I became really familiar and interested with it. So I wanted to do my own research similar to hers, but I had a little twist. I asked the question if I could do her research through a digital tool such as the quantum computer, especially since science and society is really turning towards digital things. And so what is LIGO? Because it was my biggest inspiration. So LIGO stands for the Laser Informator Gravitational Wave Observatory. And it is a large observatory and detector that has the ability to recognize stretches and squeezes in space. And when certain types of squeezes and stretches happen, that's how we detect a gravitational wave happened. So I used the LIGO experiment to understand how a gravitational wave could be present and if it was possible to utilize a digital measurement tool to compile the same information LIGO does. This here is a picture of LIGO, and this is a diagram of my interpretation of how it functions. So basically, a laser beam is sent through a beam splitter, which obviously splits the beam. And one beam goes towards this mirror and one beam goes to this mirror. And the most important part is if the beams reflect back at the same time. And so when there's a squeeze or stretch in space-time, then the distance of these lengths would change. And if one of these arms got longer, then obviously the beam would come back at a different time than the other beam. So if they did come back at different times, we would be able to calculate, oh, there was a gravitational wave at that moment in time. So now, how did I use a quantum computer to model this? First of all, this is what a quantum computer looks like, and I obviously didn't use the physical thing. I was able to use IBM, which is a quantum computer that allows researchers to create their own circuits in their own computers and send the data to professional computers. And so a quantum computer isn't really like a regular computer. Instead of using zeros and ones, a quantum computer can find like the middle superposition state that a regular computer can't. So an example of how a quantum computer works is if you had to run 52 trials to find a certain card in a deck, then you would have to just do it one by one until you got that card. But a quantum computer knows every single state that it is in and can just pick that card right away because it knows all the knowledge. So as a result, the quantum computer found the difference between the two states, or the two links of the LIGO observatory. And so if the computer measured one state significantly earlier than the other state, then we would recognize the passing of a gravitational wave. So during the data collecting part, I used IBM Quantum Composer to build circuits that would model the LIGO experiment. So first I experimented with the superposition circuit. So how I created it was the initial state, it is always something that is complementary to the other blocks. And so then I put the Hadamard's gate. And the Hadamard gate is a block that allows the reflection of both states and splits and it provides a superposition. And then the last block is the measurement block, which gets us all the results at the end. And then I also tested with the superposition with X circuit and with the interference circuit. And after each circuit was built, I was able to run the circuit through a professional quantum computer that was active, and any active computer was available, then I would just run through there and it would send back my results in a few minutes, which was pretty cool. And so ultimately the results showed me a very minuscule difference in distortion of each state. So as you can see in these charts, the difference between each state is really small. This is 526 and this is 498, and then this one is 514 and this one's 510. So they're pretty small. So it's unlikely to have said that a gravitational wave passed at that time because it could have been like a nearby microwave. It could have been anything small. And so I did have a conclusion that my computer or the IBM computer that I used was not able to detect a quantum computer, but a larger computer would be able to. And this is because gravitational waves are super big, and we would need a larger tool to detect that proportion. And lastly, through my research experience, I learned a lot about how waves can be detected and the ins and outs of a quantum computer. Using and learning about a quantum computer was lofty at first, but my mentor was a great teacher, and it was amazing to work with such a tool I never thought I would be working with at the age of 17. I also really enjoyed doing research in this field and putting my physics passions to the next level. My mentor, Dr. Thome, was an amazing mentor to work with along the way. His teaching style consisted of metaphors that really helped me understand harder topics, and his charismatic personality always made our meetings enjoyable. I would have never thought I would work with such an amazing professor and such an amazing topic. And I would also like to give a big thanks to Talaria for this opportunity because it is definitely going to be a great asset to my future. Thank you.